Hi, this is the third lecture on crystallography of materials. This time I will discuss with you about the derivation of 7 crystal systems and 14 Bravais lattices. Basically, the last time I explained to you about the two-dimensional plane lattices, basically based on one-fold symmetry, which is parallelogram. In this case, we know that the lattice point is in here, 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 but there is no symmetry around the lattice point. Another part is the parallelogram, but basically in this case, the lattice point has one two-fold symmetry. It's plane net. Okay, it's parallelogram. So there is a lattice point here, 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 here. And the basic definition of this one is the lattice point has one vertical two-fold symmetries. Last time I explained to you that when there's a two-fold symmetry in here, and when there is a translation vector, then along the bisector lines of this, and half of t vector magnitude cotangent alpha divided by 2, then there is the same two-fold symmetry generated. In the two-fold case, there is extra two-fold symmetry developed here and here and here based on the translation vectors of t1 vector and t2 vector. And from this lattice point to this lattice point, there is translation vector of half t1 vector plus t2 vectors. And this two-fold symmetry is there not because there is a lattice point. It's just the symmetry element is developed there. And again, there is a 120-degree rhombus symmetries, basically based on threefold symmetries. And in this case, there is T1 vector in here, and there is T2 vector in here. In this case, basically the lattice point has threefold symmetries. So T1 vector, T2 vector magnitude should be the same, and this angle in here should be 120 degrees. Again, I explained to you that when you have rotational symmetry and when there is perpendicular translation vectors, then another rotational symmetry develops there. And in this case, threefold symmetry is developed at this point and at this point. So this is the basis of two-dimensional plane lattices based on threefold symmetries. I also discussed to you that the same 120-degree rhombus plane net is developed when the lattice point has a six-fold symmetry. So the lattice point locates at these positions. Now we developed two-dimensional plane net. Again, this T1 vector and this is T2 vector. The magnitude should be the same, and this angle should be 120 degrees. Now, the lattice point has six-fold symmetry, and I explained to you that when the lattice point has one six-fold symmetry, and when there is a perpendicular translation vector involved, then there is a threefold symmetry developed at these positions, and along the bisector lines, two-fold symmetry is developed at these positions. Again, you have to remember that shapes of a two-dimensional plane net based on the symmetry, and you put the basic symmetry elements there, lattice points. Now you have to find out what kinds of extra symmetry is developed. Extra rotational symmetry is developed. Now there's a square plane net based on fourfold symmetry. So the lattice point is here, here, and here, and here. And of course, T1 vector is here, T2 vector is here. Of course, the magnitude should be the same. Now, because this plane net is based on fourfold symmetry, which is 90-degree rotation, the angle should be 90 degrees in here. And in this case, extra symmetry is developed at the center position. Fourfold symmetry is developed in here, and along the bisector positions of the perpendicular translation vectors to the rotational symmetry, there is a twofold symmetry developed at these positions. So these are the symmetry elements for the plane net. And so when lattice point has a certain rotational symmetry, plane net shape is defined, and also extra symmetry is developed. So you have to remember this. And also I mentioned that based on mirror plane symmetry, the rectangular plane net is developed. So the lattice point is in here, here, and in this case we put the mirror plane in here, and of course we put the perpendicular mirror plane in here. And when two perpendicular mirror plane is intersect, then two-fold symmetry is developed, which I will explain to you later. Again, when there is a mirror plane, when there is translation vectors, then bisector positions of this translation vector, extra mirror plane is developed. And if there is a translation vector in here, and if you have the mirror plane in here, then along the bisector lines, the mirror plane is developed. When the mirror plane bisects, extra two-fold symmetry is developed at these positions. And I also mentioned that there is one more plane net based on this mirror plane symmetry. That is diamond plane net. In this case, the diamond plane net, the lattice point is here, here, and here, and here. And also this lattice point is plane net is based on the mirror plane symmetry, and lattice point, there is the mirror plane intersects these lattice points, and the mirror plane intersects these lattice points. Now, this is the unit cell of the diamond structures, plane lattice of these diamond structures. Now, when there is two-fold symmetry in here, then the bisector lines of this translation vector, extra two-fold, is developed at these positions and these positions. So distribution of rotation axis and mirror planes in the 5 plane lattice types. This is the basis that we build up 7 crystal systems and 14 Bravais lattices. So far I explained to you about the plane net. So based on that plane net, now we have to develop 3-dimensional lattices. So how we develop the 3-dimensional lattices? 3-dimensional lattices is basically can be developed by the periodic repetition of a 2-dimensional lattice, plane lattice, by a third translation. So in this case, we have to define the plane lattice type, which plane lattice type we will start it. Then also we have to develop this third translation vectors. Then we can define space lattice by these manners. So the general procedure is like this. So relative placement of the 0 and first levels, I pick up one plane net, and of course when you pick up one plane net, you have to pick up the same plane net, and you put the next plane net by the translation vector of T3 vectors. So T3 vector is defined by the T1 vector and T2 vectors, the fraction of T1 vector of x, and fraction of T2 vector y, now in the g positions, vertical positions, the g. So T3 vector is basically defined by the x and y and g. Then we put the same plane net that we picked up and put it on top of that. In that manner, we can build up the space lattices. If we're doing that, basically this table shows the various informations about this crystallography. Basically, I will discuss about this part. So plane lattice type, we select first either parallelogram or rhombohedral, diamond, rectangular, square, hexagonal types of things. Then we define the third translation vector as T3 by the fractions of T1 vector and fractions of T2 vector and the G positions. By doing that, this is the systems that we defined. Basically, we define 1, 2, 3, 4, 5, 6, and 7 crystal systems. So this is 7 crystal systems that we'll define. We'll explain one by one by first selecting the plane lattice type and define the third translation vector of T3 where we put it. In doing that, we can develop 7 crystal systems. And when we're doing that, we can also define 14 Bravais lattices. Bravais lattices is basically how the lattice point locates in an unit cell of the 7 crystal system. 1P is basically parallelogram, is primitive. It's primitive starting from one fold. 1P is basically triclinic crystal system. There is a primitive triclinic crystal system. That is the definition of Bravais lattice. For instance, 2P and 2I, it starts from two-fold symmetry. So parallelogram of two-fold. Then we can define 2P and 2I. 2P is primitive monoclinic, and 2I is body-centered monoclinic Bravais lattices. So these two belongs to monoclinic crystal system, but depending on how many lattice points locates in a unit cell, now we can systematically define 14 Bravais lattices. All right, I will do it systematically one by one. Okay, I explained to you that there is a primitive unit cell. It means that there is only one lattice point in a unit cell. And there is a body-centered unit cell. It means that there is one lattice point at the corner of the unit cell, but there is extra lattice points in the body-centered position, which we will call it body-centered something. Okay, that's the definition of 14 Bravais lattices. Either A or B or C, meaning that there is extra lattice points at the center of A plane. Of course, there's two lattice points in a unit cell, and this is A-centered Bravais lattice, or extra lattice points located at the center of B plane, or either 0, 1, 0 plane. Then, of course, there's two lattice points in a unit cell. That's what we call B-centered something. Okay, so that's the definition of Bravais lattices. C-centered is the same thing. Now, face-centered, meaning that there is one lattice point at the corner of the unit cell, but at each center of the faces, there is extra lattice points. In this case, there are 4 lattice points in a unit cell, which we will call F-centered something. That's the definition of Bravais lattice. Here, something belongs to 7 crystal systems. And there is rhombohedral. Basically, the rhombohedral is just one crystal systems starting from 3-fold symmetry. But in the case of rhombohedral, there are 3 lattice points in a unit cell, and there's extra lattice points at this position and at these positions. So there are 3 lattice points in a unit cell. So that's what we call rhombohedral crystal system and rhombohedral Bravais lattice. Okay, once I explain to you, let's go systematically from symmetry 1. Symmetry 1, basically the unit cell looks like this. This is the parallelogram. There is a lattice points in here. This is the plane net, and the lattice points only has one-fold symmetry. So there's no symmetry elements in this plane net. So when I select this, and I will put the same thing on top of this, then now I have to define where I should locate the next levels. So next level of this plane net, where I can put it in. In this case, what we should consider is that when you put those plane nets on top of the first plane net, you should remember that the symmetry rotation axis is perpendicular. So the next level of plane net does not, you should follow this symmetry units of the plane net. In the case of symmetry 1, there's no symmetry elements. So you can put the next level of plane lattice at any positions because there's no symmetry elements. So T3 vector can be defined any arbitrary numbers of x and y and g. You can just put anywhere on top of this first plane lattice. Okay. In this case, basically, I can build up the plane net like this, something like this. Okay. So in this case, the lattice points located here and here and here and here. And of course, the next level plane net has the lattice points here. Now the T1 vector, T2 vector is here. Now this one is T3 vector. So T3 vector can be located at any position at any fractions of x, y, and g. Okay, in this case, this angle, alpha or beta or gamma, can have any angles. And the magnitude of T1 vector, T2 vector, T3 vector can have any numbers and any magnitude. And this is what we build up one crystal system. And this is what we call triclinic crystal system. Triclinic crystal system. So this crystal system is the definition of how this unit cell looks like in the point of x, A1 vector, A2 vector, A3 vector, or T1 vector, T2 vector, T3 vector. It can have any arbitrary magnitude. The angle can have any arbitrary angles. So this is triclinic crystal system. And when you look at it, there is only one lattice point, even though there are 8 lattice points, of course. In each unit cell, only 1/8 fraction of these lattice points belongs to this unit cell. So how many lattice points in this unit cell? There is only one. So this is what we call 1p. So this is triclinic crystal system, but when you say 1p, this is the definition of Bravais lattice. So this is primitive triclinic Bravais lattice. So crystal system is triclinic crystal system starting from one-fold symmetry of a plane net, but there is only one lattice point in a unit cell. So this is primitive triclinic Bravais lattice.